Okay, so we are looking at nucleophilic substitutions again, but this time we're looking at Sn1 reactions. So Sn1 reactions are slightly different. Our transition, say our intermediate, is different. We are going back to our carbocations. This usually involves polar nucleophiles, so something like water here, and these are typically weaker nucleophiles. And it is a stepwise reaction, so our Sn2s, they were concerted, they all happened, or all the steps happened at once. So the bond between the nucleophile and carbon was formed at the same time that the bond between the carbon and the halogen was broken. This time it's happening step by step. So we will have more steps to show in a reaction mechanism. So we'll get into it for the moment, okay? So the haloalkane of interest is 2-bromopropane. And again, we're drawing it out in such a way that we can clearly see the carbon to bromine bond, because that's what we're going to be working with. So again, carbon in an alkane is going to have a tetrahedral structure. We're popping our bromine here for the moment. We have a CH3 bound to it here. We have a hydrogen and we have another CH3. And just so we're all clear, it's this carbon, that's my central carbon here, okay? I also have water, okay, and I'm going to draw that out because I want to show my Lewis structure, because for me personally it makes it easier for me because I can clearly see that the oxygen here has the pairs of lone electrons available for bonding in its outermost valence, and this is our nucleophile, okay? So again, our nucleophile here. I do the same as I did last time. I look at the differences in electronegativity. I know bromine is more electronegative than carbon, and it's pulling electrons towards itself, giving itself a slightly negative charge. And this gives carbon its partially positive charge. Something similar is happening on oxygen, okay, because water is a polar substance, so it has two different poles, okay, so one is slightly negatively charged because the electrons have been pulled towards it by the more electronegative water, and these guys are positively charged, or slightly positively charged anyway. So what happens first? The first thing is this bromine, again acting as our leaving group, leaves, it goes, okay, so takes electrons and goes on its way. And what happens is we generate a carbocation intermediate, and we know what a carbocation looks like. We know it's carbon with 3 bonds to it and a positive charge. So what we end up with is carbon, CH3, and its hydrogen's all still there, and it's positive charge. And this is our secondary carbocation, isn't it? Because this carbon, the positive charge carbon, is bound to 2 other carbons. So this becomes a secondary carbocation. And since this is positively charged, this is now going to react with our nucleophile. Again, our oxygen has a negative charge there. These are partially positive charged. And this partially negative charge is going to be drawn to that positively charged carbocation. And what we end up with is something that looks like this. So carbon back to having 4 bonds, so that's a good sign so far. We have an oxygen here, and everything came with it. Now, this oxygen has 3 bonds. Oxygen does not want 3 bonds, it only wants 2. Okay, so it's missing some of its electrons here, so this has a positive charge here. If we were doing this in the lab, we would have a base, okay? We'd be using a base in this reaction. Okay, so we can represent our base like this, so B, which 2 electrons available. This will form a bond with a hydrogen here. It will steal the hydrogen from the oxygen. The oxygen is happy enough to let that go, so the bond breaks between the oxygen and the hydrogen. And what we end up with is our final product. Okay, so it's an alcohol. The alcohol group is on the second carbon. So this is 2-propanol. And that is our product. And we will have our base bound to our hydrogen here as well, and that will obviously depend on what base we've used, okay, but it's just a nice general formula to use. So that's the reaction, okay. So again, we need to understand the movement of the electrons or use of curly arrows or intermediates, etc. But also you need to understand why a haloalkane may undergo an Sn1 reaction and, you know, instead of an Sn2 reaction, or vice versa. So that's going to come down to the nucleophile at hand. Is it a strong or a weak one? Is it a polar or non-polar? Okay, depending on the haloalkane itself. So if you have primary, secondary, tertiary haloalkanes, that's going to dictate it as well. Tertiary haloalkanes are more likely to undergo an Sn1 reaction than an Sn2 reaction. Okay, and that's to do with the steric hindrance that we talked about earlier in the last lecture. Okay, so there's a few different things there that you need to know, and like that, noting particularly the differences in transition states. So knowing that our Sn2 reaction, we have a carbon with 5 bonds formed, okay, whereas in our Sn1 reaction we have our planar trigonal carbocation. So all of these little differences, knowing that an Sn2 reaction is concerted, it happens all at once, and knowing our Sn1 reaction is stepwise, okay, step by step. So again, go onto your problem sheets and give these a go yourself and see how you get on.